go. Yes, just for the sake of recording, I'll repeat a little bit of that. So the plan today, I'll be giving good point. How do we do that? All right, hopefully for real now. I'll be giving, some use examples of EFIT, EFITtime, and EFUND modules inside of OMFIT for the most general use cases. Specifically, I'll give a quick background on what the EFIT code does so that everyone's kind of on the same page. I will then move into how we can fetch and view, make plots of existing EFITs from either between shot, user-generated, stored in MDS+, comparing the EFIT and EFITtime modules for that. And then I'll give a basic overview of the different types of input and output files that come from the EFIT code, which will be useful when we start talking about rerunning EFIT. Specifically, I'll give an example of rerunning EFIT to try and improve an equilibrium, just as a basic example of what someone might want to do. And that will cover essentially 90% of what I think most people are doing with the EFIT code. And that part is all well established inside of OMFIT and the modules, so we essentially can go through that without ever leaving the GUI. And once we get into time permitting the last example, I will talk about making changes to an experiment using the EFUND to generate the Green's function tables and then run EFIT. And this is where things are still kind of in development. It's not quite as clean of a workflow, but it'll kind of be more forward-looking and was something that Oak specifically asked, seeing the interest that this would be something to share with more users. So jumping right in here, EFIT is a plasma reconstruction code. What that means is that it solves for a plasma description that fits the diagnostic measurements from an experiment such as D3D or elsewhere. The model that EFIT uses to describe the plasma is the Grech-Franoff equation. This is a simple, stationary, single fluid, axis-symmetric MHD model. So it makes lots of approximations that aren't in your typical plasma experiment, but what it boils down to is describing the plasma essentially in terms of three variables: the ploidal flux, psi. Specifically, the Grech-Franoff equation is cast in terms of P prime and FF prime as functions of psi, and psi as a full description over your domain, your axis-symmetric plane in this case. That basically relates these three quantities. So if you know two, you could effectively use the Grech-Franoff equation to solve for the third. But what we're doing in EFIT, we essentially don't know psi, p, or f, and we want to find all three of those variables consistently that fit the plasma measurements. So coils, probes, MSE, Thomson, anything you are using. And the way that works is by solving essentially the inverse problem of varying the pressure and the F, and then solving for psi, and then iterating on that process until you've reached a steady state, essentially. Then once you've found the equilibrium, EFIT will compute a bunch of other plasma descriptive quantities. These are the beta, the Li, the stored energy, gaps between the plasma and the limiters, strike points, secondary X points, many other things that people find useful for describing an equilibrium. And really what the main use cases for EFIT is as a transformation between a laboratory coordinate and where you are in terms of the plasma and how far in or out you are towards the core of the edge. So it kind of lays the foundation for a lot of other analyses and workflows that will be covered later in this tutorial session that can be done in OMFIT. But that's the primary use case. Additionally, if it has the option to fit the boundary, typically this is the separatrix shape. I'll give an example of this later on. But that's sort of the newer aspects of the code that aren't really as well tested and ironed out. So it's usable for that, but it wasn't really the original design. It's still a free boundary code. So even though you're fitting the boundary, it's not actually a fixed boundary. But it can be useful for design experiments if that's what you're going for. EFIT itself is described in a lot more detail in Lang's popular references going back to the 80s, but there's certainly more recent examples as well. And the figure on the right here shows an example of different diagnostics that have been set up in EFIT. Some of these are frequently used, such as the probes, coils, and MSE. Other ones, such as the lithium-ion beam and Thomson scattering, are not usually used directly in EFIT anymore. Lithium-ion beam is not a common diagnostic for equilibrium reconstruction so much anymore. And Thomson scattering, when you're trying to do a kinetic EFIT, you'll usually end up fitting the profiles of that using an external tool, sort of aligning it with the separatrix in some cases, and adding in a fast ion contribution or something else. So Oak will talk more about that in about a month, I think, 2 sessions later for the kinetic EFIT examples. So I won't cover any more about it today, but all of these can go directly into EFIT, at least in some fashion or another. My modules, so that we can look at using both of them side by side here. The GUIs, from first glance, look very similar. The options available in the operation dropdown are a little bit different. In this case, we're going to load an existing G file with the EFIT GUI and pick from MDS Plus. In EFITtime, we're going to select gather output from MDS Plus. And we'll just keep to this example shot of a D3D 163303. The first difference you'll notice is that in EFIT, you're only given the option to select one time slice, whereas in EFITtime, you can select multiple. So you can write these out in a list, or you can use a NumPy array to specify these if you wanted to do a lot more times without typing out so much. So this is just going to give 4 time slices as an example for this tutorial. And the next step, we're selecting from the tree. So in this case, I'll just use EFIT01 from the EFIT GUI. And in EFITtime, we can look at EFIT02 for something different. But you can see that there's a lot of other options for all the different types of EFITs stored in MDS Plus. EFIT01, EFIT02, and EFIT02ER are the between shot EFITs. So those are the ones you can guarantee were generated as part of running D3D. Everything else mostly is kind of flexible. It's user generated. EFIT03 typically is reserved for an after shot process that cleans up some of the EFIT. EFIT02 is sort of the MSE equivalent of EFIT03. And everything else, there's some standardization for naming schemes, but in general, they're user generated until maybe you get down to something like the RT EFITs are dedicated trees, Keiko1, Keiko2. Eventually, there'll be dedicated super facility as well, and then lots of other things users are playing around with here. But for this example, once we've selected the tree, we've already loaded the we'll have already loaded the G file with the EFUND, with the EFIT module. With the EFITtime, there's a few extra steps. Specifically, you're given the option to select A files and M files as well. You can interpolate to times that weren't saved. I know that these times actually match what the between shot 20 millisecond spacing is, so I can ignore that. Sterling actually has an open pull request for adding a script that will fetch all the available times in a discharge saved to MDS Plus. And so it'd be nice if we can integrate that into the GUI so that at some point you can just click all times if you want it. But that'll be down the road. Did you have a quick question?
Yeah, I mean, maybe it's a stupid question, but what are A files and M files?
I'll get back to that. Yeah. For now, we're just going to make some plots and see what comes up. So if you plot the G file summary, it's given on the EFIT GUI just as soon as you have one in the tree. On the EFITtime GUI, you have to move over here to the plot menu, and then you can plot the G files as well. It'll plot all of them for every time on the same here. And so you see the flux, pressure, safety factor, P prime and FF prime profiles for these example cases. And then there's several other useful plotting features that are available in the GUI for the EFITtime module. Start with, there's the chi-squared as a function of time. This essentially gives you the best quality metrics for how well converged the solution is. So the chi-squared is how well the diagnostics are being fit, broken down from total to the contribution from flux loops, magnetic probes, and in this case, MSE. Separately in this plot on top, a total chi-squared below 80 is generally considered pretty good. So none of these really seem bad in that sense. The Grech-Franoff error is the difference, maximum difference in the ploidal flux between the EFIT iterations, and the target for the MSE between shot EFITs is 10 to the minus 3, and we're below that in every case, so these are all converged. And then the magnetic axis position, you can see if it jumps in time, that's probably a sign of something that went wrong, but in this case it varies mostly smoothly along with the mean radius and Q on axis. So generally these are good quality EFITs. If there was a high chi-squared, there's another plot option in here to look at the diagnostics each specifically. We'll bring up a plot separately for every time. So we'll just plot one of them by removing them all from the menu on the right and then adding just the first time here. And then we'll plot the ploidal cross section. And what that gives you is the magnitude of the chi-squared laid out for each probe number, as well as plotted in 3D space in case you want to know where the probes are, and then all plotted on the same poloidal plane on the left. And the color bar on the left shows how high the chi-squared is. And so you can see for this case, the highest comes from this magnetic probe, which is down in this corner. Unfortunately, the fonts are not so easy to change in the automatic plotting. So you may not be able to see this very well, but this is labeled with index number 51. We'll keep that in mind because that's something that we can see if it is impacting negatively the equilibrium and try and bring this chi-squared down in the next example I go into. So to get to Raul's question, I'll go into the different types of EFIT files here. These are the main 5 types of files that you're going to interact with if you use EFIT. There's some others that we might touch on near the end. There's a few inputs that are past the command line, like the grid size. But in general, this is the different inputs and outputs. So the snap file is essentially the minimum set of inputs to run EFIT. One snap file can reconstruct any number of selected times. And what that's doing is it's telling EFIT to go fetch the diagnostic data from PT data, average it, and then slice it into every time slice specifically. And because of that, you have to have access to PT data to run EFIT with this. And it's really set up for D3D. There might be some other experiments that have a snap-like option, but in general, it's kind of D3D specifically designed. A step between the snap file and the full equilibrium solution, there's the K file. K file is another form of input to EFIT. So you can run either with snap file to generate K files, with snap file to go straight to a G file, or with the K files to go to the G file. And so the K file or R file includes all of the diagnostic measurements and other possible inputs to EFIT for a specific time slice. So you'll have a separate K file for every time with all the diagnostic information in there. So it's a much more it's a much longer, more complicated file to parse, but essentially replaces, you won't need a snap file if you're using K file. So that's generally the starting point. It's required for kinetic EFITs. If you wanted a pressure constraint, you have to use the K file. There's no just fetch pressure option from PT data. And the R file is essentially the same Fortran name lists, the same variables, but it more or less indicates whether you're running in reconstruction mode with a K file or in the boundary fit mode with an R file. So they practically could be the same, but if you get one or the other, you're expecting certain variables to be set to run EFIT in a certain way. And then the output files, there's the G file. That includes sort of the primary description of the plasma. That's your psi, P, and F. Q profile is also in there. There's a few other things we can look at when we get back to OMFIT. And it's generally an output of EFIT, but it can be used as an output to specify the boundary if you wanted to fit that. Then there's the A file, which contains all these other computed quantities from EFIT, the beta, Li, internal energy, and the M file. The M file includes sort of the description of what the measurement values are and how close the equilibrium is to fitting those, and the quality of fit, essentially the chi-squared parameter. So you can essentially, a mnemonic way to remember these, snap file is the quickest and easiest, especially if you're not using OMFIT. K file is where you would put kinetic information. R file can resolve for the boundary with different profiles. For example, a G file is sort of the most general output of EFIT. An A file contains auxiliary information, and the M file is measurements. This is all documented in much more detail on our GitLab page.
Is there a P file? Because I thought I heard Oak mention this.
P files are created by the profile fits. So not generated by EFIT, but they can be related because there's the mapping involved when you're fitting profiles. So they often go hand in hand, but doesn't actually involve EFIT. I don't know what happened. Here we go. So this is our GitLab documentation. And here we have the input name lists. This, if it wants to go, has at the top here all of, yeah, it's not happy. It has all of the descriptions of the variables inside of the name lists. Outputs then also describe the G, A, and M files. So if we come back online, I'll show that later. That's the files. So now to give an example of running EFIT, we'll return to our project here. Rather than continuing with these modules, I'm actually going to just import a clean EFITtime module, work with EFITtime going forward because of some of the additional functionality it has, but you can certainly rerun EFIT with the EFIT module alone. So we're going to go through this process of selecting the operation. This time we're going to select generating the K files from snap file. You could generate the G and K files from snap directly, but you don't have as many options. There's just not as well set up in the GUI. So we'll actually use K files as an intermediate step. Select the EFIT02 like we did before. Now we see more information about setting the averaging times for the MSE, magnetics, loop voltage, and whether you want to enforce those constraints. This has to be done as the data is fetched and put into the K file. You can't necessarily go back and redo this without regenerating your files. Whereas the solution, relaxation, and convergence, we can edit the K files before we run EFIT. So you don't necessarily have to worry about these at this stage. For now, we're just going to leave them as is, generate these files. So EFIT's now reaching out to PT data, fetching for these 4 time slices that we specified, and putting those into K files. And so once we have that, now go to the generating G file from K file option, where we'll have a lot more control over how we want to generate EFIT. So you can change the grid size. Again, we have the relaxation and convergence, and also the maximum number of EFIT iterations. These are the 3 parameters that, or 4 parameters that you can change quickly and easily to see if they improve the convergence of an equilibrium. Sort of the first stab at something that doesn't converge is probably to play with these, but may not work in every situation. And so coming back to our example here, where we have a probe that stands out with the high chi-squared, this was number 51. So down in the bottom here, we have the constraints options, and we can change what the weights are on these magnetic measurements. And so if we select probe 51 from the list here, what we can do, change that weight from 1 to anything smaller, but for this example, we'll just do 0. Plotting that shows that this probe down in the corner here has been turned off. It's red, so it's got a 0 weight. And we could just run this on Iris like we were before. But to do something a little fancier, what I'm going to do is actually change where we're running EFIT. Some modules will default to running on a system where the code is installed. And if you're trying to run somewhere else, it'll just automatically switch the server that's running on. For the EFIT modules, you need to actually go in and specify which server you're looking at. So I right-clicked here and went to set up module. And now you can see the server is pointing to Iris. We could change this to Omega if you won't have access and can run there. For something a little more interesting, I'm going to try the nurse system Perlmutter. And anywhere that EFIT is installed and set up in OMFIT, you'll be able to select that server and run on that. These are the 4 portals, another one at NSTX, and soon we'll have an ALCF machine Polaris set up. But what this is going to do is, instead of running the EFIT version on Iris, it's just going to run it remotely. You see we've lost the option to use anything from snap files because out on NERSC, it can't connect directly to our PT data. There's a firewall that prevents that. So this is one reason that the K files being able to be transferred between systems seamlessly with OMFIT is useful. And with the EFITtime GUI and module, normally EFIT is run in parallel. So every time slice will be launched as a separate job in a job array. And that'll make everything go as fast as possible normally. But on the nurse systems, there's many more users, the queue is much longer. And so if we were to do that, we'd be here waiting for a while. So we can actually turn that off, just run everything in serial, just for this example. And that's what we're gonna do when we hit generate G files down here at the bottom. Yeah.
But I mean, this job you could run on the debug queue, right? Because you're only doing time slices if you wanted to.
You
Full
could.
time slices. Because
So right now you didn't see we specify anything about the queue. The queue is essentially hidden inside the module. So you'd actually have to go in and make some changes to do that. The default is to run on the normal queue. But in many cases, you could get away with debug if you're a super user. So you see that if it ran, we got outputs downsynced from Perlmutter. So everything is back now on Iris, and all our files are in the OMFIT tree here. M file, G file, A file, K files are in inputs along with the snap file. Once again, if we look at just this single time slice like we were before, where we had a total chi-squared of 41, magnetic chi-squared of 25. If I make another plot, it'll just kill that one, so I'm going to close it. I missed my add and plot.
You want to say how you figured out? We were looking at your.
Oh, yeah. If you saw this error message pop up, it says no time selected. That's because this list was empty. So here we've reduced from 41 to 32, the total chi-squared. Magnetic chi-squared went from 23 to 18. And if we zoom into this corner, there's no longer probe 51. You see the largest chi-squareds now come from these two MSE channels, and the probes are sort of at a similar level. So that could be a sign that that probe standing out like that was either averaged poorly for this shot. It was maybe measuring something erroneous. Hard to say for sure, but certainly you could improve chi-squared further by eliminating more diagnostics, and in doing so, you're probably actually going to have less constraint on your equilibrium and get something that gets pretty weird after a certain point. But to see how it looks, we can plot the G file. We can do the same from our last EFITtime module. Try and compare these two side by side. You probably won't see much of any difference. So to make a little bit nicer plot, what we can do, start using the tree a little bit. The original EFITtime module, you double click the G file, you'll get the plot of the flux surface like we saw before. Go to the new one, double click that, it'll bring up another plot. But if you instead right click, quick plot is what the double click does, but quick over plot will put these two on the same axes. Now you can see them right on top of each other. There's a small change in the pressure profile, pretty minimal for the most part. Some change in the flux near the outside of the separatrix in the open flux region, but generally speaking, a pretty small change from this. So while we're in the tree here, we can look at a G file. The variable definitions aren't always clear. Psi, this is the 2D flux matrix, P prime, FF prime, sort of as expected. These are the general descriptions of the plasma, but you'll see some other option lists down here as well. The aux name lists is something that can be appended to a G file. It's not uploaded to MDS Plus, so you won't always see it. Along with some of these other variables, KVTOR and mass, they can be generated by EFIT, but they may not always be, so they're not stored necessarily in MDS Plus. You won't see them if you look at an already generated EFIT. but these are all part of the actual G file, whereas aux quantities is actually all OMFIT computed flux surface or other useful quantities for analysis. So the flux surface specifically does averages of a lot of different quantities around the flux surfaces that can be useful for analysis. But these aren't actually part of a G file. They're computed by OMFIT, and when you read in a G file as part of the workflow, they get added to the tree. So that is something to watch out for. It's a useful feature, but if you're giving someone a G file, don't expect them to have this same flux surface necessarily.
Is EFIT AI version of the default version when you're launching EFITtime?
It is.
Okay, so
It is.
you want the legacy to check that box.
Yep. You'll see. Well, I should have gone to the other one. Yeah. Yeah, the legacy option, it's not available on Perlmutter, but it is on Iris, and that's the only place right now. Maybe on Portal. Yeah, Iris and Portal. That'll sort of default, that'll change the version of EFIT, but in general, you shouldn't see much difference doing that. Sort of another super user feature there. And so,
Sure. What is the difference
yeah.
between the EFIT AI and the legacy?
The legacy EFIT has not been changed in at least the last 4 years, probably going back further. EFIT AI is generalized so that it can run more than just D3D. The legacy version will only run one specific machine and then have to be recompiled for every experiment that it's applied to. So those are some differences. We've improved the performance of the newer version. As the name AI suggests, we might eventually add in a machine learning accelerator, but right now nothing like that exists. Right now it's the same algorithm just being sort of modernized in the coding.
Forever name consistency.
Yeah, we've checked consistency.
You improved it, right? Cleaned it.
Yeah, in a lot of cases. Yep. Mm-hmm. So that covers what most people probably are interested in doing in EFIT, with some permutations for your specific case. I'm going to go kind of quickly because we're nearing the end of the talk here, but now we'll get into sort of the more unusual stuff, things that aren't done as frequently in OMFIT. So what we're going to do, I'm going to load the EFUND module. And what EFUND does is it computes the green function tables that EFIT is using to relate the measurements in coils to the plasma or each other. And so this essentially describes where the sensors and coils are in the experiment and the impact that they have. And by changing that, you can modify an experiment or in principle, generate something totally new. For this example, I'm just going to modify something existing for the sake of time. We have a lot of different templates for different machines that you could start with. In this drop-down list from the GUI, we're going to go to similar D3D, slightly newer than what the previous example was, but more or less the same. So EFUND actually is slower to run than EFIT. It's sort of a pre-processing step that has been separated from the solve to make EFIT run as fast as possible. So when we ran before, we used green function tables that were deployed on the systems as part of the EFIT installation. And so we didn't have to worry about doing this. But we'll use low resolution to speed things up. And so just with the GUI, you can plot here the D3D coils and probes. If you wanted to actually go in and see what all these are, there's the option to use labels in this plot. And what's important is that for the boundary fitting way of running EFIT, it only varies the F coils. So the F coils in this are the orange blocks. All the other blocks outside of that are E-coils or A-coils that can be specified with a fixed value when EFITs run, but EFIT won't try and manipulate those to fit the boundary. So we can only actually change and make a difference in these orange coils when we're going to run. So for this example, we're going to see which of these coils, if we just sort of move it way away from the plasma, would have the biggest impact. Anyone following along have a good idea which one or two those might be? And for the sake of time, I'm going to go ahead and give you the answer. It's going to be the coils closest to the separatrix, the X point, down here in the diverter. If we zoom in, these are numbers which I'm sure no one can see. 13 on the left, 16 in the middle. We'll remember those numbers because now we want to move those coils. There's no option in the GUI to do this. It's an undeveloped area right now for general users. So we're actually going to have to manipulate this mhdn.dat file, which describes all of the machine. It's documented in the GitLab page that I was trying to show earlier. I accidentally deleted. And so the names aren't always obvious, but what we're trying to do is change the radial position of the F coils, which is described by this variable RF. And so to manipulate it, since it's 18 element array, the quickest and easiest thing to do, copy its location and then use the command box. So here in the command box, I'm going to control V to print, set that elements 13 equal to something large like 3.5 meters. Copy that and then do the same for coil number 16. We'll put it in a slightly different place. We'll put it a little bit closer to 2.5. Once we put code into this command box to execute, we hit this button. And if you look closely, this the mean and max values actually changed. Max is now 3.5. And if we go ahead and replot the coils, you'll see those two changed. We put one way out here and the other here, no longer in near that separatrix region. And so we're going to run EFUND to generate these green function tables. And doing this will give us a different description for when we're going to rerun EFIT and try and fit the boundary.
Can I ask you a dumb question?
Yeah.
I see that you changed the values through the command box, and I think you could have changed it through just right clicking and edit, correct? Is there a preferred, just as a scientist, do you have a preference on which way you edit your studies?
If it was a scalar value, you can edit and you just have one value to change. So that's pretty easy. If you have an array of values, then you kind of have to go in here and count positions, and it's maybe doable, but not quite as simple. So the command box for arrays is kind of my preference. Yeah.
So can I choose the MHD input file local from my local user?
We could pick a different one. You can pick locally, or yeah, the templates are just sort of a starting point. Yep. Jihan.
Based on the output, so did it actually recompute all the Green's functions, not just the response of the F coil and the, okay.
Does everything all at once. There's not really a separate option for one, just updating one. That's partly why it takes so long. It's a good point. Now, if we go back to our EFIT module, so this is not set up in EFITtime. Once you're doing the boundary fit option, it's really only set up in EFIT. It's kind of hard to specify multiple G files to fit different boundaries at different time slices. Probably could be done, but right now it doesn't exist. So instead of loading like we did before, what we're going to do is go to modify equilibrium. And to use the green functions we just generated, there is now a custom green function option right here in the GUI. What that does is it changes from using the system located green function tables to using the ones in the EFUND module at the same level in the tree. The R file, you can define yourself, pick one from a location in the tree or a file. We're just going to use default here. You're given more options to make some changes. In some cases, it gets unhappy if you don't set the shot, even though the shot is kind of irrelevant when you're just creating something yourself. We generated the tables at 65 by 65 resolution, so that's the only one that'll work. Anything else would fail. Convergence is much easier to get to higher convergence when you're just fitting the boundary and not all the diagnostics. So we can leave that at default higher error. Also generally runs faster, so 100 iterations is quick. It automatically selected the G file that we had already loaded from the first step. We could select a different one. And there's an option to pick an A file. You want some different ways to set up the plasma quantities. There's a bunch of options here if you wanted to change things. So you can change plasma current. You can shift major, minor radius, scale the profiles, change the magnetic field. So there's quite a bit of flexibility if you just want to change something by hand. Furthermore, if we had used an R file, there's the option to specify a boundary in there. What we're doing is loading the boundary from this G file. If we had specified it in that R file, you could actually turn this off and modify a shape manually, where you'll have, you'll just throw an error. But, well, didn't throw an error. You can actually just click and drag these points to change the boundary shape by hand if you wanted to do that. For now, we're going to fit that same boundary. We're going to use just what's in the G file and hit modify to run EFIT. And that just finished. We can plot the G file summary, and what this will do is actually compare the EFIT that we had read in that we're trying to fit the boundary for to the new one. And you can see that by eliminating these coils down here, you're no longer able to generate that X point at the same location. So it tries to fit the shape everywhere else as close as possible with the remaining coils, but as a consequence, the X point has to get pulled out by a different coil. And so you get a little bit of different change there. So this is kind of just a wonky example of what you could do. Certainly you can try and play other games with moving coils closer or further and seeing how that impacts things.
Speaking of games, just as a thought exercise, could you fix this now by going and adjusting the weight of those two coils and setting them to 0, and then that might just pull the X point back toward where it was supposed to be? Or
it wouldn't, because the coils are in totally different places. So
but what if you put a 0 weight for the fitting to those coils? Does that not just take them out of the fitting simply, or the
they're
squares?
probably mostly out of the fitting, being this far away from the plasma anyway. The problem is that you no longer have any coils down in this region to pull the plasma closer
The
to.
absence and not so much
Yes.
the modified.
Yes. You could do something similar by changing the weights and turning these off, I think. But this is one of many things that you can play around with in this module. The only other thing that I was going to demonstrate while I had this open comes to mind is that there's also an export option. You can save to MDS+, that'll add an EFIT number X+1, and you can name it as you like if you want to distribute that. Once something's added to MDS+, it can't really ever be removed. It can be hidden, is my understanding. So that option is not recommended unless you have a really good reason. But you can also convert to OMAS. So OMAS is the open source implementation of the IMAS hierarchical data schema for describing plasma. All of the EFIT files can be converted to that, both directions with OMAS. And there was an option in the operation list to run EFIT as using the input from an OMAS file. Those are options that are available. But essentially what this is just going to do is give you an ODS in your tree once it finishes that has all of the time slices saved into a single file type here. So you can see inside the equilibrium time slice, there's 4 entries. First one is the first time, 2.4 seconds. In the profiles, you can see things like pressure. The names are much more easily interpreted in IMAS, and double clicking just plots as a function of the array element index. And you can see essentially the same pressure profile we saw before. To save an OMAS file, you'd have to, again, use the command box. But if you wanted to save, for instance, this G file somewhere else on your system, you can go to the deploy option and it'll bring up an option to save it in some location on the file system, either locally, or if you have access to a remote like Perlmutter, I could go save files there if I wanted to. So we're near the end of time here. Takeaways, hope you've been able to see is that there's many ways to do these analyses, and OMFIT offers some really useful utilities and can make powerful workflows for doing these things easier. And so with that, happy to take any other questions or comments. Yeah, will be.
So for the boundary fit, do I understand correctly that it's taking a target boundary or whatever the G file on my hand and then trying to come up with a set of core currents to make that boundary happen?
Exactly.
Okay.
Yep.
Okay. And then does the internal part of that fitted result obey Grad-Choronov?
It does. It does. So it's still using the Grad-Choronov description, and it's also taking the P prime and FF prime profiles either from that G file or as specified in the input file. So you're essentially setting those as well as functions of the normalized flux. So as the plasma flux mapping differs, those profiles will be shifted a little bit, but you're essentially trying to get to the same thing that you specify. And Nathan.
So for EFUND, the example you gave was moving one of the build coils. Could you also use it to move like one of the magnetic sensors and see what the effect of it is?
Yep. Yep. You can change basically any of those constraint options doing that. There's options for vessel walls, wall elements as well. That's where those are communicated with EFIT. So you could move vessel elements if you had a model for the current in those, play games with that. Running EFIT will generate the synthetic measurements. So even if you don't have a measured value for a new probe location, you can get the synthetic signal there in the M file. One quick note that I missed mentioning, K files, they aren't actually saved for D3D in the MDS Plus. You can only pull snap files and then the outputs. That's just because the between shot EFIT doesn't actually generate K files, or didn't used to, and was never set up to save those. So if you want a K file, you essentially have to use the snap file that's in MDS Plus and generate those running EFIT. It's a little bit different other places. So at NSTX, they save the K files. You can pull those directly from MDS Plus. So that differs a little bit, machine to machine. I guess another thing, there's a bunch of other snap file options if you wanted to make something different. Well, it's not gonna work on that one. You can find those instead of using the MDS Plus database, you can use an extension. So these are sort of known snap file descriptions. JTA_F is kind of what's used for magnetics between shot right now. There's a whole bunch of MSE. The 23 is what the latest one is, but you can go back and snap files from many other types directly in the GUI if you wanted to do that as well. And yeah, I think that's all I was planning to cover today. Shihan.
2 questions. So is there a documentation somewhere that explains what these cryptic things mean for the snap file
Yeah,
names?
there's a little bit of some of that. Oak started putting in, I think it's for the A file, there's this desk description. So that's a whole separate menu that just has documentation. It's not the most complete or up to date, but it gives you a quick and easy starting point for figuring out what these things are. The documentation I was hoping to show here, now that this page loaded, also has all of these variables for the input name lists on this page. And if it loads, we'll see G files, A files, and M files. All the variables are described on this GitLab page that I had in my presentation. This is the most up to date. We keep this as current as possible. So most complete and up to date is in here. Joey. It's under the modules, OMFIT.io.
What did Joey ask? I couldn't hear it.
If it's linked on the OMFIT website. Your modules. Go to, it should be in both EFIT and EFITtime now, but down in here for external resources under the official web page, you can find it there as well. Good point.
So is the difference between EFIT and EFITtime with these 2 modules? Just in EFIT, you just run one time, whereas EFITtime, you run as many as you like?
At the highest level, that's the big difference. Yep. There's some minor changes in terms of what options you have in the GUIs. You can't run modify, like fit boundary modify mode in EFITtime.
Yeah.
You only do that for one-time slice, but generally speaking,
That's that thing you did with the Green's functions. You went to EFIT instead of EFITtime, right? So,
correct.
Are there other versions of EFIT outside of OMFIT? And what does ops use?
That's a good question. So the history of EFIT is unfortunately pretty long and involves a lot of forked versions. Ops right now for between shot is using the newest version of EFIT. So it's the EFIT AI version that is the default in OMFIT. So currently that's what's being run. For older shots, it was older versions. Generally speaking, there's been one lineage at D3D, short of the break between the legacy now that we're still sort of keeping around, but will be depreciating soon, hopefully, and EFIT AI modern version. But once you start talking about other experiments, there's actually an EFIT installation for Eater, for NSTX, and those have kind of proliferated